Astronomers for generations have been looking at the sky, and of course we've done multi-wavelength, multi-energy astronomy. So we look in the optical, or we look in the infrared or the radio, or we can go to higher energies and look in the X-rays and gamma rays.
However, once you reach wavelengths as small as high energy gamma rays, the sky is not transparent, it's opaque to light. So we know that there is at least 20% of the universe we have never seen.
And so multi-messenger astronomy, in particular neutrinos, using neutrinos instead of light or photons, has the promise of being able to look at energies well beyond what we can do optically.
Neutrino astrophysics is a very exciting field because neutrinos are so numerous out there, and they play an essential role in many phenomena like supernova explosions, or the formation of galaxies, or the life, birth and death of stars.
The neutrinos we see today come from sources going back to the beginning of the universe and come from throughout space.
Yet they are among the hardest to catch particles. And this poses the greatest challenge to an experiment that is actually searching for astrophysical neutrinos.
IceCube was the first experiment of a cubic kilometer in size that was able to see a diffuse astrophysical flux of neutrinos.
Nobody had ever built a kilometer cube detector, never mind a neutrino detector. And of course the motivation was to prove that it was large enough to see the cosmos in high energy neutrinos. And we indeed proved this was possible. So how did we do it? Well, it's interesting, the detector was already there. It's a block of ice, highly transparent. Blue light travels 100 meters to more than 200 meters throughout its volume. So it's what physicists call an ideal Cherenkov medium. It's shielded by 1.5 kilometers of South Pole ice, shielded from radiation at the surface and cosmic rays. So all we had to do was instrument it.
The construction of IceCube is a huge challenge, and it's a many-year effort. So, I mean, the first articles that were written about the possibility of IceCube were, back in late 80s, early 90s, and we started construction in earnest in like 2003, 2004. And once you get into the construction mode, it's all about schedule. And in our case, the bottleneck was installation of instrumentation deep in the ice at the South Pole.
We filled this kilometer cube of natural Antarctic ice with 5,160 photosensors, which are basically 10-inch photomultipliers which you buy in Japan. The real problem was to put them in the ice and to figure out how to read them out. And so we solved that problem. It took a while, but IceCube is ticking like a Swiss watch right now.
I went to Pole twice as a grad student to help with the construction of the detector, and I went last year to install some scintillator panels in a R&D project for future upgrades. Every task has a risk, which I think is amplified by the fact that the environment is unique. It is quite high, but it's very cold, very dry, and very isolated. So even simple hardware installation can be challenging.
Very challenging, very difficult, a lot of hard work, a lot of pressure, and we had fun.
The big question now is where and how are neutrinos produced?
There is a type of event that we are looking for. It's called the glacial resonance. It sits at a certain energy where interactions are more likely than at other energies. So we actually should find it. But you never know. I mean, it might not come. And if it doesn't come, that's also fine for us, because then it's a new opportunity to rethink models and make new models and open new windows to eventually new physics. I mean, that's always what gets people excited, me as well. The possibility that there might be something hiding in the data that opens the window for new physics.
There's the science, there's the ultimate thing that you want to do, the knowledge you want to bring to the scientific community, and then there's the day-to-day excitement of what you're doing. And it's the kind of thing you can't do by yourself, you know, in a lab down in the basement. This is something where you need a dedicated group of people with a common goal and interest to work together collaboratively to do science that otherwise you couldn't do.